Hi everyone, welcome back to my YouTube channel. I am Reeti and I am back with another lecture in the DBMS series. So in the last couple of lectures we learned about indexing and types of indexing. In this particular video we would be learning about B and B plus trees. So without any further ado, let's get started. So before starting with B and B plus trees, let's just understand that why do we even need to learn about them. So clustered and non-clustered indexes are concepts that describe that how the data is stored and accessed in our database. So it tells us that how the data is stored and how we can access the data. But B trees and B plus trees are the data structure that actually implement these indexes. So the implementation of these indexes are done using B and B plus trees. So knowing B trees gives you insight into how these indexes work under the hood. So it helps us to tell about the implementation of these indexes. Now understanding B trees helps you to understand that why certain queries perform very well and poorly based on the structure of the index. So based on the structure of the index, we can determine that why a given query is performing very poor or very great. So for example, how a B tree or balanced nature affects search times or why range queries are efficient with B tree indexes. So the balanced nature of B trees help us to get our data retrieval very fast, and it also help us to search for the range queries. Now B trees provide the balanced, efficient structure that makes these type of indexes performant, ensuring that the operations like search, insert, delete and update are done in logarithmic time. So all the CRUD operations like create, read, update and delete are performed in logarithmic type whenever we use B tree data structures as part of our indexes implementation. So these makes B tree indexing crucial for optimizing database queries, whether in a clustered or non-clustered index scenario. So it really helps us to get all those CRUD operations performed in the logarithmic time, which is such a great time complexity, and we can get our data very fast. Now what is this B trees? So B trees is also called as a MV tree, where M defines the order of the tree. So we'll be learning about order of the tree in next set of slides. For now you can just understand that B tree also is called as MV tree, where M represents the order of the tree. So B tree are self-balancing tree data structure that maintains sorted data and allows searches, sequential access, insertion and deletion in logarithmic type. So all the CRUD operations are performed in a logarithmic time. Also all leaf nodes are at the same level in the B trees. So all the leaf node or the last node are at the same level in the B trees. Now in B tree you can minimum have 2 children and maximum x children, where x is the order of the given tree. Order is also represented using M, but here I am using x for reference. So x children. Now B tree is a generalization of a binary search tree. So if you don't know about binary search tree, I'll suggest you to go ahead and have a look on what is a binary search tree, because if you have a basic concept on binary search tree, B tree and B plus tree would be really easy to understand. Now in binary search tree, every node can have at most 2 children. That is, if this is a can either have 0 children, 1 children or 2 children. In the B trees we can have at max of x, or you can say m children, that is the order of the tree. Also here there would be only one key which would be present in each node, but here there could be multiple keys which is present in our nodes. Now let's learn about the structure of a B tree. So the first one is node. A B tree is composed of nodes, each containing keys and pointers to the child nodes. So this is a node which contains a key, as well as block pointers which references to the child nodes. So these are the child nodes and these are the block pointers which references to the child nodes. Along with the key we also have a data pointer. Now what is a data pointer? So data pointer or record pointer is the one where the record is present in the secondary memory. So data pointer or record pointer help us to know at what particular location our record is present in the secondary memory or the disk. Now the keys within a node are sorted in ascending order. So all the keys which are present within a node are sorted in ascending order. Now root, internal nodes and leaves. So the root node is the topmost node in the tree. So the topmost node in the tree is called as a root node. Now coming to the second one, that is internal nodes. So internal nodes contain keys and the child pointers. So these are the internal nodes after the root nodes, which contains the key as well as the child pointers, or you can say the block pointers. So these are the block pointers. Now coming to the third one, that is leaf node. So leaf node contains key and possibly pointers to the record of other data. So this leaf node also contains key and the block pointers, and these particular block pointers, when there are no further nodes, it points to the null. So these are the keys which are present here and it points to the null. Along with the keys, we have a data pointer which tells us where the record is present in our secondary memory, or you can say disk. Now in indexing, each key in a B tree node typically represents a value or range of values, and associated pointer directs to a data block where the record is present corresponding to the key can be found. So for example, in a database, the key might be the value in a column and the pointer might be direct location to the row or a set of rows in a given table. So here we can see that all the nodes are having the same structure. They are having key, they are having the data pointer associated to the key, then they have a block pointer which corresponds to the address of their children's, and here it is the root node. After the root node, all the nodes are the internal nodes, and then at the last one we have the leaf node which also has key and data pointer. Now a B tree of order x can have the maximum number of children a B tree can have is x, that is the order of the tree. So the maximum number of children any node can have is the x, that is the order of the tree. Now coming to the maximum number of keys. So the maximum number of keys for every node is x minus 1. Now why it is x minus 1? So consider here the keys are provided k1 and k2, and here we have provided the block pointers. So at max I am saying that this particular tree can have only 3 children. So we'll have 3 block pointers, 1, 2 and 3, and here you can see that we have only provided 2 keys because there is 3 block pointers. So we can say the number of block pointer is the maximum number of children the key can have, or the order of the key, and the number of keys is order minus 1, that is x minus 1. Now coming to the minimum number of keys. So the root node can have minimum 1 key. The other nodes apart from root can have ceiling of m by 2 minus 1. Now what is this ceiling? So ceiling tells us the upper value. So consider if I am dividing 8 by 2. So it is giving me 4. But consider I am dividing 9 by 2. It is giving me 4.5. So it will take the upper value of 4.5, that is 5, and 5 minus 1, it will give me 4. So whenever we want to find the minimum number of keys, for root node it will always be 1. For other nodes it would be ceiling of m by 2 minus 1. Now what are the minimum number of children? For the root node we can have at most 2 children. For the leaf node we won't be having any children because leaf node is the last node in the tree. And coming to the internal node, we will be having ceiling of m by 2. This is the minimum number of children internal node can have. Leaf node will be having 0 and root node will be having 2. The minimum number of keys in the root node would be 1, that is there would be only 1 minimum number of key. The other nodes can have ceiling of m by 2 minus 1. The maximum number of keys every node can have is x minus 1, where x is the order of the. So insertion in B tree always happens from the leaf node. So you have to make sure that whenever you are inserting any value in the B tree, it always happens from the leaf node. It doesn't happen from the root node. So we have to insert the value only from the leaf node. If it overflows the value, then we push it to the internal nodes or the root node, but the value insertion start from the leaf node itself. So let's take a node of a binary tree. Now in this particular node, we will be having a block pointer which contains the reference to the child node. Then we have a key, and then we have a data pointer which contains the reference for the record in the disk. So what we will do is, this is the node. Now in this particular node, how many block pointers can be there? So the block pointers is equal to the order of the tree. So at max, the order of the tree is considered 3. So there will be 3 block pointers. So here there will be a block pointer BP1, then there will be a key K1 D1, then there will be again a block pointer BP2, then there will be a key K2 D2, and then so on. There will be multiple block pointers as well as key and data pointers. Now consider that if someone provides you the block size, the block pointer size and data pointer size, how you can find the order of that particular tree. So this is the block size, like this particular block has a size, so that is called as a block size. Now this is the block pointer size and this is the key as well as the data pointer size. You can derive the formula for the same. So here m is the order of the tree and the number of block pointers depends on the order of the tree. If the order of the tree is 3, then there will be 3 block pointers. If the order of the tree is 5, there will be 5 block pointers. So we will multiply m with pb, where m is the order of the tree and pb is the block pointer size. Now coming to the key as well as data pointer. Now key and data pointer are always 1 less than the order of the tree, because there are some block pointers and there are some keys and data pointers, and keys and data pointers are always 1 less than the block pointer. So it will be m minus 1, that is order minus 1, into k stands for key and PD stands for the data pointer size. So we will add this key and data pointer size together, and then we will multiply it with m-1, that is order -1, and that should be less than the block size. So here the number of keys a node with m children can have maximum of m-1 keys. Number of block pointers, each node has m block pointers to the child node. Number of data pointers, each key has an associated data pointer, so there are m-1 data pointers. So the data pointers and keys are always m-1, that is 1 less than the block pointers, and the block pointers are always the maximum of the order of the tree, that is x or m, that is the order of the tree. Now let's say you have a block size B of 1024 bytes, you have a block pointer size PB as 8 bytes, you have a data pointer size PD as 12 bytes, and you have a key size K as 16 bytes. Find the order of the tree. So you have to find the order of the tree. So we'll come to that formula where we will multiply order of the tree with the block pointer size, that is PB, that is 8. Then we will subtract 1 from the order because the key pointers and data pointers are always 1 less than the block pointers. So that is m-1. Then we will add the key pointer as well as the data pointer, that is 16 plus 12, and that is always less than and equal to block size, that is 1024. So here we can find the order of the tree is 29. So in this way we can find the order of the tree when all these values are provided to us. So what are the steps to insert values into the binary tree? So first one is start at the root and recursively move down to the tree to find the appropriate leaf node where the new value should be inserted. So as I told that insertion in the binary tree always happens from the leaf node. So we have to find the leaf node where we can insert the value. Now second one is insert the value into the leaf node in a sorted order. So we have to insert the value into our leaf node in a sorted order. If the leaf node has fewer than the maximum allowed keys, that is order -1, this step is simple. So consider that if I have to insert 1, 2 and 3 and this is my leaf node. Now this particular leaf node doesn't have any data at all. So what I'll do is insert 1 and then I'll insert 2. But consider the order of this particular tree is 3. So the maximum number of keys which can be inserted is m-1, that is order -1. So 3 minus 1 is 2. So we can only insert 2 keys at max in the leaf node. But consider that if I have to insert 3 also, then how the insertion will happen? So if the leaf node contains the maximum number of keys after the insertion, it causes an overflow. So what we have to do is we have to split the nodes. So divide the nodes into 2 nodes. The middle key median is pushed up to the parent node. So what we'll do is we'll find the median of this, that would be n by 2. So we'll find n by 2 and we'll find that 2 is the median node. So it will be pushed to the parent node, and then once it's pushed to the parent node, it can hold 2 elements. To the left of this particular parent node, we will be having 1. To the right of this particular parent node, we will be having 3. So this will be a lesser value than 2 and this will be a greater value than the parent node. So the left half or the original node stay in the place while the right half forms a new node. So insert the median into the parent. If the parent node also overflows after this insertion, recursively split the parent node and propagate the median up the tree. So the fourth one is if the root node overflows. So consider the node in which I am inserting the data, and because of this I am pushing the data to my parent node. Like whenever I am inserting the data into my leaf node, if the leaf node is overflowing, I am inserting or pushing the data into my parent node. But consider that the parent node also overflows and the parent node is the root node. Then what we should do in that case? So which can happen if it already has the maximum number of keys, split it into 2 nodes and the median becomes the new root. So what you have to do is you have to split it again into the 2 nodes and then the median becomes the new root. So we can say that this increases the height of the B tree by 1. So this will increase the height of the B tree because earlier we had only 2 particular levels, but now we have 3 levels. So let's see that how we can create a B tree of a given order and how we can do the insertion of the values into our B tree. So create a B tree of order 3 and insert values from 1, 4, 6, 8, 10, 12, 14 and 16. So the maximum number of children a tree can have is equal to the number of block pointers, which is equal to the order of the tree, that is order of the tree is 3. Now coming to the maximum number of keys a given node can have, that is order -1, that is 3 minus 1, so 2. So the maximum number of keys a node can have here is 2 and the maximum number of children a node can have is 3. So insertion in B tree happens from the leaf node and the values are also inserted in sorted order. So the element in the left of the root would be having less than the root and the element in the right of the root would be having greater than root. So if this is the root and any element which is inserted in the left of the root would be having lesser value than the root and the one which is inserted into the right of the root would be having a larger value than the root. So step 1. Start at the root and recursively move down to the tree to find the appropriate leaf node where the new value should be inserted. But this is a new tree which we are creating, so we will be starting from the leaf node. So we have to insert the value into the leaf node in sorted order. So the first value is 1, I've inserted 1. The second value is 4, I have inserted 4. So if the leaf node has fewer than the maximum allowed keys, that is order -1, the step is simple. So this step is simple. We have inserted 1, we have inserted 4. But here it is told that the maximum number of keys a node can have is only 2. Now we have to insert 6. So how can we insert 6? So what we will do is, in the step 2, if the leaf node contains maximum number of keys after the insertion, it causes an overflow. So split the nodes, divide the nodes into 2 nodes. The middle key, that is median, is pushed up to the parent node. The left half of the original node stays in the place while the right half forms a new node. So 1 and 4 is already inserted in my node. Now I have to insert 6. But here the maximum number of keys a node can have is 2. So I have to insert 6. So what I'll do is, I'll find the medium including the 6. So that would be n by 2 because the number is odd. So the median would be 4. So what I'll do, I'll push 4 to the parent node, and then 4 will be created as a parent node, and in the left of 4 I'll be having 1, and in the right of 4 I'll be having 6. So this is how we split the node and we push the median of the node to the parent node. So here you can see that we have created a new node, that is a parent node. Now in this node the left of 4 is having 1 and the right of 4 is having 6, because this value should always be less than the parent node and this value should be greater than the parent node. Whenever there is a overflowing which happens, push the median of the node to the parent node. Now we have inserted the median into the parent node. If the parent node also overflows after this insertion, recursively split the parent node and propagate the medium up the tree. But here the parent node has not overflowed. So now we have to follow the step 2 again to insert other elements. So we have inserted 1, we have inserted 4, we have inserted 6. Now we have to insert 8. 8 is greater than 4, so it will come into the right of 4, so we'll insert it here. After 6, 8 is inserted. Now we have to insert 10. Now again the same situation is coming where we are overflowing the data. So because of which what we'll do is, so we'll push the median to the parent node and we'll create a new node in the right to insert 10, as 10 is greater than 8. So here we have pushed it to the parent node and here we have inserted 10. So to the left of 4 we are having 1, to the right of 4 we are having 6, to the right of 8 we are having 10. Now we have to insert 12. So we can insert 12 to the right of the 8 because it is greater than 8, so we have inserted 12 as well. Now we have to insert 14, but how we will insert 14? Here the data is already overflowing, so we'll send the median to the parent node. But now parent node is also overflowing, so we have to push the median element of the parent node to the root node. So what we will do is, we have pushed 8 here. Now to the left of 8 we are having 4. Now 4 is having 1 and 6. To the right of 8 we are having 12. Now we are having 10 as the left of 12 and 14 as the right of 12. So let's understand from here what we have done is, here we have pushed 12 to one step above. So here 12 is here and 4 is here. Now here, since there were 3 elements again which was overflowing, so we have pushed the median 8 to one more above node, that is a parent node. So here we have pushed 8 here. Now to the left of 8 we are having 4, to the right of 8 we are having 12, to the left of 4 we are having 1, to the right of 4 we are having 6, to the left of 12 we are having 10, and to the right of 12 we are having 14. So in step 3, if root node overflows, which can happen if it already has a maximum number of keys, split it into 2 nodes and the medium becomes the new root. This increases the height of the binary tree by 1. So here we can see that the height of binary tree was having only 2 levels, 0 and 1, but here the height of tree has been increased. So this is how you can do an insertion in our binary trees. Let's learn about the deletion in the binary key. So in the insertion, we were saying the maximum number of keys a given node can hold. But in the deletion, we need to see the minimum number of keys a given node should have. Because consider if I delete all the values which is present in our node, so it will be violating the binary key rules. So we have to search for the minimum number of keys which a node can have. So here we are considering a binary tree of order 4. So the minimum number of keys is ceil of m by 2 minus 1, that is 4 by 2 minus 1, that is 2 minus 1, that is 1 key. So when the order is 4, the minimum number of keys a node can have is 1 key. So let's start. So the step 1 is, begin at the root and recursively move down the tree to find the node that contains the key to be deleted. So So we'll start from root and then we will search for the key which needs to be deleted. Now the step 2 is consider the case where the key is a leaf node. So we have to consider a case where we have to delete a key which is present in a leaf node. So first one is simply remove the key from the leaf node. So what we have to do is first we have to search for the key which we need to delete, that is 10. So we'll come here and we'll see the root is 40 and 50. So the key that is 10 will be less than 40. So we'll come in the left and here we have found the 10. Now here what we have to do is we have to delete 10, but we have to make sure that the minimum number of keys remains 1. So is the minimum number of key remaining 1 after deleting 10? Yes, so we can simply delete 10. So if the node still has the minimum required number of keys, the deletion is complete. So the deletion is complete because it still has the minimum number of keys which is required. Now coming to the case 2 where the key is in the leaf node, but there could be a possibility that if I am deleting that particular key, the node is having less than the minimum number of required keys. So consider here I am deleting 20. So if the deletion causes the node to have fewer than the minimum number of keys, proceed to the borrowing or the merging step. So we have to follow a borrowing or the merging step. Now how we can follow that? So here I have to delete 20, right? But if I delete 20, the minimum number of key which is needed is 1. That would be violated. So what I'll do is, if the node has a sibling with more than minimum number of keys, you can borrow a key from the sibling. The parent key between the node and the sibling moves down through the node. Here I have to delete 20. What I'll do is I'll find the sibling, immediate sibling of 20. So there are no siblings in the left, there are some siblings in the right. Now I'll see that if the number of siblings is having more than the minimum number of keys, so the minimum number of keys is 1 and the sibling is having 2 keys, so we can borrow 1 key from this particular sibling. This node A can borrow a key from node B so it can maintain the minimum number of keys. So this particular borrowing happens via the parent node. So what happens here, we are deleting something which is in the left of the parent node. So we'll be picking the smallest value from the parent node. So here it is 40 and 50. So we'll be picking 40. We will be giving 40 here. And then we will be deleting 20, and from here, since parent needs to maintain the 2 keys because it has borrowed from the sibling, not from the parent. So from the parent we will pick up the maximum value and we will go ahead and provide it here. So now it will be 4750. Here is 40 because we have deleted 20 and here it is 44. So the minimum number of keys is maintained here as well and here as well. So there is a borrow which has happened between these 2 siblings via the parent, right? Now here you would be thinking that why we are sending the smallest value here and why we are borrowing the largest value here. So here we are deleting from the left node of the parent. So left node always contains the smallest value. So from here also we will be using the smallest value so that this particular root and parent node does not have any unbalanced or unsorted way in which the data is stored. So we will give 40 here and here we will pick the largest value because here we are replacing the key from the right of this particular 40, right? So from the right of this particular 40, if we are replacing the value, we need to pick up the highest value. So we'll pick 47 and we'll put it here. Now consider another case that the key is again a leaf node, but when we are deleting a given value or a given key, it can't even borrow from the sibling because sibling also has the minimum number of key. So consider that I have to delete 40. And I can't borrow from my sibling because sibling also has the minimum number of key which is required. If I borrow from the sibling, it will be short of the key, right? So in that case, merging happens. So if borrowing is not possible, that is the sibling also has the minimum number of keys, merging the node with a sibling happens. Now the key from the parent that separates the 2 nodes move down into a newly merged node. If this causes the parent to have too few keys, repeat the borrowing or merging process at the parent level. So what we will do here is we will merge this 40 and 44, and from the parent node, which is a common between these 2 keys, that is 40 and 44, that is 47, will come down and perform in this particular merging. So it will be 40, 47 and 44, and then we can go ahead and delete 40. So what happens is merge the node with the sibling. The key from the parent that separates the 2 nodes move down in a newly merged node. So it will be 50, 44, 47 since we need to store our data in a sorted manner, and here it will be 52 and 59. So this is how the merging happens when the sibling doesn't have more than the minimum number of keys, and this is how borrowing happens when the sibling has more than the minimum number of keys. Now coming to the next case, when the key is an internal node. In the last case we saw about the leaf node. In this case we'll be seeing about the internal node. So here we have to delete 20. Now 20 is an internal node here. So how the deletion happens? So what we do is we replace the key with its predecessor, the largest key in the left subtree, or its successor, the smallest key in the right subtree. So here we have to delete 20, but the minimum number of keys which is required for a given node is 1. So if we delete 20, it will violate the binary tree rule. So how we can delete 20 when 20 is an internal node? So what we will do is we will replace the key with its predecessor or successor. So we will replace it with its predecessor or successor. What is predecessor? The largest key in the left subtree. So we'll go into the left subtree and we'll find the largest key, that is 10 and 11. So we'll replace 20 with 11 and we will delete 20. Here we can replace it with 11 because the minimum number of keys which is required is 1. So here if there is 10, the minimum number criteria is matching. So delete the predecessor or successor key from the corresponding subtree. So we can delete this particular key which is a predecessor or successor to this particular 11. Now if this causes an underflow, the node has few keys, proceed to the borrowing and merging step. So if this particular causes an underflow, we have to go to that borrowing and merging step. Now consider if we have to delete 11 and 11 is the minimum number of keys a node can have is only 1, and if we delete 11 it will violate that property. So we have to do that borrowing and merging step which we discussed in the leaf node. In the same way it will happen here as well. Now let's learn about B plus tree. So a B plus tree is an extension of B tree and is commonly used in databases and file system to maintain sorted data and allow for efficient insertion, deletion and search operations. B plus tree is also a balanced tree, meaning all the leaf nodes are at the same level. So in B plus tree also all the leaf nodes are at the same level. It is a balanced tree. Basically it is an extension to the B tree. Now here I am saying that B plus tree is an extension to the B tree. Then what are the common differences between B tree and B plus tree? So the key difference between B plus tree and B tree lies in how they store the data and how the leaf nodes are structured. So there are some differences in how they store the data and how the leaf node of them are structured. So the very first one is, in B tree all the actual data or references to the data are stored in the leaf nodes and internal node only stores the key. So in B plus tree what was happening was every node was storing key, data pointer and block pointer. The block pointer points to the children, the key points to the value, and the data pointer points to the address where the record is present in our hard disk. Now in this particular B plus tree what happens is, in leaf node only we store the key and the data pointer. In other internal nodes we only store the key, not the data pointer. So only in the leaf node we store the key and the data pointer, and there is only one block pointer which is present per node which points to the next leaf node which is present in this B plus tree. So in B tree what used to happen was, there was a key, there was a data pointer, there was a block pointer, and this particular block pointer used to point to null when it was a leaf node. But in B plus tree there is key and data pointer, and then there is only one block pointer per node which points to the next node which is present in this leaf. Now coming to the next point, in a B plus tree leaf nodes are linked together in a linked list fashion. So they are linked together in a linked list fashion and they use the block pointer for the linking purpose. Now each leaf node can have only one block pointer which contains the address to the next leaf node. So this is how the leaf node looks. It has key, it has data pointer, and it has block pointer which addresses to the next leaf node which is present in the system, and it follows a linked list fashion. During inserting the value in B plus tree, a copy of the key is always stored in the leaf node. As I told that the internal nodes only have the key, it doesn't have the data pointers where that particular record is present in our disk. All the details are present in the leaf node only. So what will happen that whenever we insert any value in the B tree, the leaf node always have a copy of that particular node in the leaf node in a sorted manner. So here if I am inserting 30 and 70, in the leaf node I'll be having a copy of 30 and 70. Because in the leaf node we have the data pointers, in the internal nodes we don't have any data pointers, we only have key. Now coming to the internal node. So internal node do not store data pointer, only keys and the child pointers. So in the B tree what used to happen was, there was a key, there was a data pointer, and then there was a block. But here what happens is, in the internal node there is only key, there is no data pointer which is present, and there are some block pointers which points to the child nodes. So this is how the internal node is designed in B plus tree. So this allows more keys to be stored in each internal node, leading to a lower height and more efficient operation. Now data pointer don't needs to be stored, so the amount of size which data pointer was consuming is reduced. So we can go ahead and insert more number of keys in B plus tree rather than B trees, and this will help us to have a less height of the tree rather than B trees. Now what is the structure of B plus tree? So the first is root node. The top node of the B plus tree which points to the first level of internal nodes or directly to the leaf nodes if the tree has only one level. So this is the root node which points to the internal nodes, and if there are only two levels of nodes which are present, then it points to the leaf nodes. Now coming to the internal nodes, these nodes contain only keys and pointers to the child node. This node only contains key and the block pointers, or you can say the pointers to the child node. It doesn't contains any data pointers, it only contains the key. So it will be K1, K2, K3, K4, and in between there will be some block pointers for this particular children's. Now coming to the leaf nodes, so these node contains keys as well as data pointers. So the leaf node contains keys as well as data pointers, and there is only one block pointer which is present which points to the next leaf node, enabling quick traversal of records. So all the records is present in the leaf node only. If we want to search for any record, we have to just go to the leaf node and traverse the leaf node and find that particular record. What are the advantages of B plus trees? So B plus trees have a balanced structure, meaning all the leaf nodes are at the same level. So all the leaf nodes would be at the same level. This balance ensures that the search operations require logarithmic time relative to the number of keys, making it very efficient even for the large data sets. So even there are large data sets, we store all the data in the leaf nodes, so the traversal is very easy and we can find any data. Insertion, deletion, and like reading of the data is performed in the logarithmic time. Now coming to the second point, the structure of B plus trees allows for direct access to the data. Since the internal nodes contain only the keys, searching for a specific value can be done quickly by navigating through the tree down to the leaf node where the data is stored. So in the leaf node, since the data is stored and the internal nodes only have the keys, the leaf node have the key as well as data pointer, and it also has a block pointer which points to the next leaf node. So it helps us to get the data very fast, and the traversal is also very easy. This was all about B and B plus trees in this particular video. I hope you like this video. So if you like this video, please hit the like button. If you're someone who is new to my channel, can go ahead and watch out the tech content first. And if you find it useful, can go ahead and subscribe. Also, if you have not followed me on my social media handles, you can go ahead and follow. The links are in the description. Till then, take care, keep learning, keep growing, keep smiling. Bye all.